Dear learners, welcome to another session on Green's theorem. In the previous lecture, we verified Green's theorem where R is a circular region. In this problem, we will be verifying Green's theorem where the region R is a square region. So the boundary is going to be 4 straight lines. We call them as C1, C2, C3, C4. Now before proceeding into the problem, let's recall what the statement of Green's theorem. It says that closed integral over C f1 of x comma y dx plus f2 of x comma y dy is double integral over R dou f2 by dou x minus dou f2 by dou y dx dy. Now the boundary of the square region R is closed, obviously, as we see in the figure O A B C O. It's a closed figure. Now let's proceed to verify the Green's theorem. So if you consider the LHS of the Green's theorem, it is integral over C f1 dx plus f2 dy. Now it can be split into 4 simpler regions, simpler boundaries C1, C2, C3 and C4. Therefore, the left hand side integral is going to be the sum of 4 integrals. Integral along C1 f1 dx plus f2 dy plus integral along C2 f1 dx plus f2 dy plus integral along C3 f1 dx plus f2 dy plus integral along C4 f1 dx plus f2 dy. As we have seen in the statements of Green's theorem, the boundary could be finitely many linear curves or straight lines. So now along C1, that is along OA, we see that y remains 0 throughout. If you look at the coordinates, at O it is 0 comma 0, at A it is 1 comma 0, so y remains at 0, whereas your x varies from 0 to 1. Therefore integral along C1, the given integrand takes the form wherever x comes, wherever y comes, we replace by 0 and dy is also 0 and we retain x. So the integral takes the form x squared dx. So on integrating we get x cubed by 3 between the limits 0 to 1. So on applying the limits we get 1 by 3. Now along C2. So along C2 means it is along AB. Along AB we see that the coordinates to be 1 comma 0 and 1 comma 1. Coordinates of A is 1 comma 0. Coordinate of B is 1 comma 1. That is, x doesn't make any change. There is no change in x. X remains at 1. So x is equal to 1. Because there is no change in x, we get dx equal to 0. Now at A, x is equal to y is equal to 0 and at B y is equal to 1. Therefore y varies from 0 to 1. And so the integral over C2 of the given integrand takes the form wherever x comes put 1, at dx replace by 0 and retain y and dy. Okay, so it is y squared, there is a mistake, x we give x is equal to 1, so x square becomes 1 and y square remain as y square, so it is 1 plus y squared dy. So it is 1, integrating we get y plus y cube by 3 between the limits 0 to 1, so it is 1 plus 1 by 3. Now along C3, that is BC, from B to C, what happens? At B the coordinates of B is 1 comma 1, coordinates of C is 0 comma 1. That means y remains as 1. So y is equal to 1, and because there is no change in y, dy is 0. And we see that x varies from 1 to 0 because at B x coordinate is 1 but at C x coordinate is 0. So x varies from 1 to 0. So the integral along C3 of the given integrand takes the form integral along C3 the given integrand x squared plus xy dx plus x squared plus y squared into dy takes the form integral 1 to 0. So wherever y comes replace by 1 and dy is 0. So we have x squared plus x dx. Integrating we get x cube by 3 plus x squared by 2 under the limits 1 to 0. So in the upper limit it becomes 0. So substituting the lower limits minus 1 by 3 minus 1 by 2. Now along C4, that is from C to O. So coordinates of C 0 comma 1, coordinates of O 0 comma 0. That means x remains at 0. There is no change in x. Therefore x is equal to 0 and hence dx equal to 0. So from the coordinates we see that y varies from 1 to 0. So the integral over C4 of the integrand takes the form. So in the integrand wherever x comes replaced by 0 and dx is also replaced with 0. So the resulting we get 1 to 0 y squared into dy. So integrating y squared we get y cube by 3 under the limits 1 to 0. So we have minus 1 by 3. So the LHS is sum of all these integrals. So closed integral over C, the given integrand x squared plus xy dx plus x squared plus y squared dy, it is equal to integral along C1 plus integral along C2 plus integral along C3 plus integral along C4. So it is 1 by 3 plus 1 plus 1 by 3 minus 1 by 3 minus 1 by 2 minus 1 by 3. So cancelling out the terms that are equal in magnitude but opposite in signs, we get 1 minus 1 by 2, which is 1 by 2. Now let's consider the right hand side. So right hand side is the double integral over R, dou f2 by dou x minus dou f1 by dou y dx dy. So from f1 let's compute dou f1 by dou y, it's nothing but x, and from x2 which is x square plus y squared. So on partially differentiating with respect to x, dou f2 by dou x, which is 2x, and substituting in the right hand side of the Green's theorem we have, and along the region which is a square region, so all the four limits are going to be constant. So x varies from 0 to 1 and y varies from 0 to 1. Here we have taken the horizontal strip. So dx is evaluated first and then the dy. So the left hand side of the Green's theorem, double integral over R dou f2 by dou x minus dou f1 by dou y dx dy takes the form integral 0 to 1, that is the limits of y, and then integral